Hello friends, myself Rohit Tate, and here I'm going to start with the new course, that is Digital Electronics and Logic Design. So to study this course, we need to be aware with the bits and gates that are used in the digital electronics. So first thing, let me introduce you the digital bits. Digital bits are 0 and 1. So using these two binary bits or digital bits, we can perform any operation on the logical gates. Now, which are the gates which are used in digital electronics? So there are some basic gates and some derived gates. So we'll see one by one. So first of all, digital gates are digital gates. So first AND gate, OR gate, NOT gate. So these are AND gate, OR gate, NOT gate. These are known as basic logic gates. Then NAND gate, NOR gate, XOR gate, and XNOR gate. These are derived gates. So we will see the logical symbol, truth table of each gate. So first of all, let me start with the basic gates. Basic gates, AND gate. The symbol of AND gate is like this. Two input AND gate. It is having two inputs. Let's assume A and B are two digital inputs applied to AND gate. The AND gate symbol is like this. It is having two input and one output. Let us assume Y is the output. So for these two inputs A, B, we have to find out the Y, that is output. So for that we are going to write the truth table. Truth table for AND gate. So in truth table we are having two entities, inputs and outputs. So inputs are A and B. So write their names here, A and B, and output is Y. So these are three entities that we are going to write in the form of truth table. So input A, B and output is Y. So for A and B, for two inputs, we are having four possible combinations of binary bits 0 and 1. So we have to take each possible combinations of binary bits for these two inputs. So first combination is 0, 0. Then second combination is A0, B1. Third combination is A1, B0. And the last possible combination is A1, B1. So for all these four combinations, we are going to write the output as Y. Suppose if I am applying this A as 0 and B as 0, then the AND operation between A equal to 0 and B equal to 0 is 0. For second combination, A equal to 0, B equal to 1, A equal to 0, B equal to 1, Y is 0. Third combination, A equal to 1, B equal to 0, output is 0. Last combination, A equal to 1, B equal to 1, output is 1. So this is the logical symbol of AND gate, and this is a truth table of AND gate. Now second basic gate that we are going to discuss is OR gate. Now first let me draw the symbol of OR gate. Again OR gate with two inputs and one output. Let us assume A and B are inputs and Y is the output. Now we are going to write the truth table for OR gate. Again, it is having two inputs A, B and Y is output. So again we have to write the four possible combinations of binary 0 and 1, and last is 1 1. So for A equal to 0, B equal to 0, if we apply 0 0 here, then the output of OR gate is 0. When A equal to 0, B equal to 1, output of OR gate is 1. A equal to 1, B equal to 0, output of OR gate is 1. A equal to 1, B equal to 1, output of OR gate is 1. This is truth table of logical OR gate. Now the third and the last basic gate, that is NOT gate, and its symbol is like this. This bubble indicates the inverter. It is having only single input and single output. A is the input and its complement is A bar. Its input and output, we are writing the truth table. So if it is having only one input as A and the output is complement of A, so for single input variable we are having only two possible values of 0 and 1. One is 0, second one is 1. So for A equal to 0, its complement is always 1, and for A equal to 1, its complement is always 0. So this is a truth table of logical NOT gate. Now these three are the basic gates. Now the next part, that is the derived gates. In derived gates we are having four: NAND gate, NOR gate, XOR gate and XNOR gate. So we will see one by one. So first, NAND gate. These NAND gate, NOR gate, XOR gate and XNOR gate are known as derived gates because by using basic three gates, that is AND, OR and NOT gate, we can derive them. That's why these are known as derived gates. So the first is NAND gate. So NAND, within its name there is a meaning. So NAND, it's a possible combination of AND gate and NOT gate. So this is AND gate with two inputs. Suppose inputs are A and B. The output of this AND gate is A and B. Now this output we will apply as an input to NOT gate, and here we will get the final output as A dot B complement, and that is the NAND gate. So here in this NAND gate we have used one AND gate with two inputs and one NOT gate. The final logical symbol of NAND gate for two input is like this, and with one bubble, and this represents the NAND operation, A dot B complement. This is a NAND gate symbol. Again, its truth table for two inputs A and B, we will write down the output. Again, two inputs, four possible combinations: 0 0, 0 1, 1 0, 1 1. So for these two inputs we will having outputs. What is AND operation of 0 0? It is 0 and its complement is 1. 0 1 AND operation, 0 1 0, its complement 1. 1 0 AND operation, 0, its complement is 1. 1 1 AND operation, its complement is 0. So this is the truth table of NAND gate. Similarly, we will discuss NOR gate. Again, NOR gate, it is a combination of OR gate and NOT gate. So this is OR gate with two inputs, A and B. Output is A or B. This is a representation of OR operation. Now this output I am going to assign to NOT gate, and the final output is NOR, A plus B complement. Now final logical symbol of NOR gate is like this. For two input NOR gate, this is the logical symbol of NOR gate. A and B are inputs and output is A plus B whole complement. This is a NOT gate. Now let me write the truth table for two inputs. A, B are the inputs, Y is the output. So for two inputs, again we are having four possible combinations of 0, 1. Those are 0, 0, 0, 1, 1, 0, 1, 1. For these four combinations, I am going to write down the output value. What is OR operation between A and B? A or B? It is A equal to 0, B equal to 0, 0 or B, 0, and its complement, it is 1. Then A equal to 0, B equal to 1. There or 0 or 1, it is 1, but in NOR we have to take its complement, so it is 0. 1 or 0, it is 1, but in NOR we have to take its complement, that is 0. 1 or 1, it is 1. In NOR gate we have to take its complement, that is 0. This is a truth table and logical symbol of NOR gate. Now the next derived gate is XOR gate. XOR. So how to write XOR? The logical symbol of XOR gate is like this. This is the logical symbol of XOR gate for two inputs. And the equation we can write in this form: Y equal to A complement B plus A B complement. In simplified form, we can write this equation in this form. This is the XOR symbol, A XOR B. And its truth table is like this. For two inputs, A and B, we are going to find out the output in XOR operation. 0, 0. Again, I am going to take four combinations: 0, 1, 1, 0, 1, 1. In XOR operation, out of two input variables, if any one of them is 1, then output is 1. And if out of two input variables, both are similar variables, means both the variables are having similar values. So in this table, row number 1 and row number 4, we are having similar values for both the variables. In that case, output is 0. And in row number 2 and 3, we are having complement values, means out of two variable, one is 1. At that time, output is 1. So this is a truth table of XOR operation. And the last derived gate, it is XNOR. And its logical symbol for two input is like this. Inputs A, B, and output is Y. Its logical equation we can write in this form: A XOR B whole complement. In simplified form, we can write down A XNOR B. This is the XNOR operation symbol. Again, the truth table of XNOR gate for two input A and B. Let me write the four combinations of 0 1. Now, what is first in XNOR truth table, we are going to find out the XOR value for two variables, and then finally we will take its complement, because in equation you can observe it is a complement of XOR operation between A and B. So what is XOR operation for A equal to 0, B equal to 0? Already I told you, if both the values are similar for two variables, output is 0 in XOR, but in XNOR we have to take its complement. So if both the values are 0, in XOR it is 0, but in XNOR it is complement value, that is 1. Similarly for row number 4, both are similar. In XOR it is 0, but in XNOR we have to take the complement of XOR, so that's why it is again 1. And any one of them is 1, then it is 1 in XOR. So in XNOR we will take its complement, so it is 0. So this is a truth table for XNOR gate. So in this way we have discussed the basic logic gates and derived gates. Let me revise once again. There are three basic logic gates: AND gate, OR gate, NOT gate, and derived gates: NAND gate, NOR gate, XOR gate, XNOR gate.